Welcome to the last party of the training on numerical computing with Rust on CPU. As you know, this training is co-organized by NCC France and NCC Slovakia with the participation of IGC Lab, the National Supercomputing Center of Slovakia, and Sona Lake, and Adrien Graland is going to share all the vision of how to use Rust for optimization around the grayscale Scout reaction. So, Adrien, if you want to start for the last part of your training.
Thanks a lot, Karim. So maybe today I would like to start with something a little different and just show you some nice pictures, because as we mentioned, that's what this is about, right? So what you are seeing here is a program that performs the grayscale reaction simulation in real time on GPU and renders it also in real time inside of a window using Vulkan. I wanted to show this just to stress the point that even though yesterday I said that I think Rust is a bit too young for production when it comes to GPU computing, and I do think that, it's already ripe for some experimentation. And this particular experimentation was quite insightful as far as I'm concerned for two reasons. The first reason is that the interesting part here is that actually my computer has an AMD GPU. And anyone who has ever tried to do GPU computing on an AMD GPU knows that their official GPU compute stack called ROCm is unfortunately not the highest quality software you've ever met. So it was much of a surprise to me that in contrast, their Vulkan video drivers are actually extremely good. And with a Vulkan program, I just got the thing working almost on the first try, and all the bugs I found were on my side, not on the side of the implementation. And what was even more of a surprise is that later we ran it on a computer of my colleague with an NVIDIA GPU, which was not the one on which I did the development. And it just worked right away without any modification. And it provided performance that was competitive with his own optimal. No, that was the good part. The bad part is that raw Vulkan is quite a bit more effort to write than a typical CUDA program, which is why personally I would be waiting for some higher level layer on top of Vulkan before attempting to implement more sophisticated numerical simulations in it. But yeah, as you can see, it can be made to work. It already produces competitive performance. It enables real-time visualization use cases very easily. It works on multiple hardware. So I'm quite happy with it and interested to see how this will pan out in the future. Now, since yesterday I did the grayscale introduction a bit late, I know that some of you could not follow it, so maybe let me go over it a bit again. So, so far in this course, we've been introducing the use of Rust for numerical computing. We saw how C++ is, in my mind at least, the main competitor to Rust in the numerical computing ecosystem. We had the occasion to compare them across many axes, see how Rust is better in some areas, worse in others. And then I guided you through an introduction to the usage of Rust for numerical computing, starting from the very basics of the language and going all the way to what you would need to have some linear algebra, to implement some linear algebra primitives like the dot product. And hopefully I have convinced you that at this small scale, I mean, Rust is pretty fine to use. But obviously, you know, we all have linear algebra libraries at hand. We don't often need to implement our own primitives. So it would be good to also see how Rust can handle more realistic computations. Which is why we are going to talk about Grayscott, but not, unfortunately, what used to be until recently the first link you get when you search for Grayscott on Google. Instead, I'm talking about the Grayscott reaction-diffusion model. The general idea of this computational model is to treat chemistry as just a simple cellular automaton. So you say, okay, we have a species of kind U and V, chemical species that can be atoms, molecules. And if we end up in the situation where one occurrence of species U is surrounded by two occurrences of species V, then U will turn into V through a chemical reaction. If we only simulated this phenomenon, it would not be that interesting because soon enough we would have consumed all the U in our initial simulation domain, and we would be full of V. Which is why we will add a few terms to the equation. We will add a source term that lets us regenerate U over time, a drain term that lets us remove some of the generated V product so that the simulation does not end up full of the V product. And some diffusion term for the sake of realism, because in nature, it's not actually realistic to end up with lots of U in one place and no U elsewhere, for example. There are all sorts of physical forces that tend to smooth out the concentration of the species in space over time. And finally, we are not going to simulate each molecule atom individually. That would be too costly because in chemistry, we are typically manipulating quantities of matter in the order of the Avogadro number, so 10 to the 23 particles. That's too much even for our big supercomputers. So instead, we are going to simulate the spatial concentration of the species. And when you do that, you get this system of two coupled differential equations. So here you can see that there is a term that consumes U and creates V, which is proportional to how much U you have and how many pairs of V you have. We have a term that creates U. As you can see, it's a bit more complicated than that. We will not get into the details, and they are not very important. Overall, the idea is just to stabilize the simulation so that you don't get an overflow of one of the species over time. We get another term that removes V over time because there's a negative sign here in the temporal derivative. And then we get diffusion terms that tend to smooth out U and V in space over time. And now, once we have these differential equation, the million-dollar question is how do we solve these equations to get the time evolution of the spatial concentration of U and V? And as it turns out, actually, these kind of partial differential equations that couple temporal and spatial derivative are quite tricky for mathematicians. And right now, we do not have a proper formal resolution method that will give us results except in very easy spatial cases. Which is why we must turn to the dark side of mathematics and start introducing some approximation. And then we leave formal analysis and enter the realm of numerical analysis. Since this course is about programming, not numerical analysis, we will use a very simple mathematical scheme, and I will hope the mathematically inclined of you will forgive me for this. So we will just discretize space via a finite difference scheme, which means that basically we will be considering finite regular grids that we will, for simplicity, just simulate a 2D grid, which is easier to visualize. We will only compute values of the concentration of species U and V on points of that regular grid. And we will say that in this situation, the spatial derivative of the U and V concentration is approximately the difference of neighboring grid values divided by the grid state. Here I'm hand waving a bit the full gradient computation, but those who know will know, and those who don't know, I will provide the pre-made code anyway. We will discretize then time using a similar scheme called the Euler's integration method. So the idea is that here we say that given knowledge of the concentration of U, say, at a given time t, we can deduce an approximation of the concentration of U after some extra time delta t has elapsed by just taking the concentration at time t and adding to that the amount of time that elapsed multiplied by the time derivative of the concentration as given by the previous equations at the initial time. Our goal here will be to produce some pretty pictures. More precisely, we will be saving the output of the simulation for one of the chemical species into an HDF5 data cube like a good numerical scientist would. But for the sake of easier debugging and nice visualization, we will then post-process this HDF5 data cube into a set of nice-looking PNG images where basically each time step of the simulation will be turned into one PNG where the lighter color represents higher concentration of the V species. We will also, along the way, try to achieve some secondary goals, like we would like to control some of the simulation parameters via command line arguments for, to experiment around without needing to recompile the program every time. We want to report progress as we go through the simulation. This will allow us to see how quickly the simulation is going without waiting for it to end. And because this course, a big topic of this course is CPU performance, we will also attempt to take this simulation as close as possible to peak CPU performance. Before we move on, I would like to remind you that I would like us to use the Q&A section if possible. So I see in the chat that there has been some issues with the Q&A. I hope they are resolved by now. To me, at least, they seem to be working normally. But basically, using the Q&A helps me see better what's going on with the questions, because as soon as many people start talking in the chat, it becomes a bit unreadable. So I see that there has been in the chat one question from John. What are some alternatives to static 2D spatial representation? Would one discretize space with higher resolution in areas where more information is expected? Indeed, that's one option. Then we enter the whole realm of adaptive grids, a numerical method. There are also some discretizations that do not use regular spatial grid at all, but instead, for example, you discretize over Fourier components of the solution of your simulation. This is quite a big realm of applied mathematics. And to be honest, I'm not extremely knowledgeable about it myself. Usually I go for more knowledgeable colleagues when I need help in these areas. But basically, here what I wanted to stress is that finite differences and Euler's method are just arbitrary choice that I picked for simplicity. And you should really, if you are solving some differential equations yourselves, you should really spend some time studying the mathematics of that, because there are many options that I did not go into. Well, it looks like the Q&A issue resolved itself. Meanwhile, that's good. So I would actually like to, for us to go through the first chapter of this practical work together as well, because there's actually not that much work for you inside of this one. And its main purpose is to introduce you to the amount of code that I have already written for you before the start of the practical so that you can move faster. So let me do that. Because this program, Grayscale simulation, starts to be a little larger, I have tried to write it a bit less like prototype code and a bit more like the kind of code I would like to see in production programs. So for example, I have tried to separate the implementation into multiple modules, one dealing with data storage, one dealing with saving in-memory data to disk, also putting compute kernels separately. And then I try to introduce these code modules one by one. So first, the first thing I highlight is that we are going to manipulate some floating point data in memory. And in the end, among the two floating point types that are easy to use in Rust today, 32-bit IEEE and 64-bit IEEE, the choice is, well, kind of arbitrary, right? It will guide how precise we are, but we might want to use reduced precision for performance reason, as on CPU it usually gives us 2 times performance advantage, and on GPU it can be even faster. So there are several different ways to approach this issue of not making a final decision on a floating point precision right away. The one I personally prefer is to have a type def somewhere in the program which centrally defines which precision you are using. I find this to result in code that is much cleaner than making everything generic over the type of floating point number in use. So I do such a type def, and here also I introduced the pub keyword, which is used to make elements of a code module public so that other modules in the program can use them. By default, everything is private in Rust, like class members and methods in C++. Then, using that floating point type, I define storage for concentrations of the U and V chemical species. We are always going to manipulate these two together, so it makes sense to group them into a single data structure. And we do not actually need this data structure to be encapsulated, right? Because we do not have some common invariant. Well, we kind of do, but let's say that they are not super important. In the C++ program that this Rust program was derived from, the initial concentration was hard-coded, so I replicate this. This is also an occasion for me to show you how a bit how object-oriented programming works in Rust. So here I define a method, and I can have so-called impl blocks, which allow me to associate methods with this data type that I have just defined. When I do so, I have access to two variants of self keyword, one in capital and one lowercase. The capital version allows me to refer to the enclosing type. Like here, this is my constructor method. It receives as a parameter how many rows and columns our grid has. And as far as output is concerned, it returns one UV struct. I also define another constructor that zero initializes the memory. You can use it as a faster alternative to the new constructor in cases where you don't care about the precise shape because you are going to override the data anyway. And then I define an example of an object method, which I call shape. And this takes an object of type UV by reference, and it returns an array of two numbers, which tells me what is the shape using usual mathematical convention. So first rows, then columns. After this, I need to manage the question of how I handle evolving concentration of my chemical species. I could opt to create one UV object per simulation step. But every time I do so, I need to allocate two two-dimensional arrays. initialize them. And this can get a bit costly. Well, we could avoid the initialization part using unsafe code, but we don't actually need to, because we can use a very common pattern from graphics programming called double buffering instead. And the way double buffering works is that now I can define another data structure called concentration. And this time you see that I do not expose the members publicly because I have some invariants to take care of. And what this does is that this struct internally holds two pairs of concentration grids, two concentration grids for U and V. And it also holds a Boolean, which tells me of these two, which one I will consider to be the source concentration, the output of the previous simulation step, and which one I will consider to be the destination concentration, the storage in which I will write the output of the next simulation step. The constructor to this double buffered object simply offloads to the constructor of UV. The initial source term is as defined by the reference C++ implementation, and the back buffer, so to speak, the one that we will use to compute the next simulation step, is zero initialized because we don't care about its initial value. I expose the shape information again, just offloading it to the first buffer. It doesn't matter which one I pick because they have the same size. I have a method which allows me to read the current concentration. This uses the Boolean, which tells me which is the current front buffer and back buffer, and then I use that to read the current concentration. When that Boolean is false, this will return 0, so 0 is the first buffer, and when the Boolean becomes true, this becomes 1, and then I will access the second buffer, and so on. I will flip between them. How will I flip? Actually, because to use this object now, the user side looks like this. So I have a method called update. And this one, unlike the previous ones, requires a mutable reference to the concentrations object. And the reason is that it allows us to change the concentration. The user of this update method provides a callback, typically a closure, but it could also be a free function, which receives as a parameter first the current concentration, and second, another UV struct, which is where the new concentration is to be written. The code then makes sure to call this user callback appropriately for the current double buffer configuration, either using the first or the second UV concentration as a source concentration and the other concentration as a destination concentration. And every time such a time step is taken, then I need to flip my Boolean so that I switch the role of the source and destination. All this to say that it was a bit of work to write this abstraction, but in the end, on the user side, it results in relatively clean code where the simulation engine does not need to care at all about this whole double buffering things. It can just, in a loop, as long as needed, call concentration.update, get the current concentration, write the new concentration. Here in this dummy code, it simply copies the old concentration into the new. That's obviously not correct. And then at the end of the simulation, I can read the final concentration by using the current method. On top of this, I then implement some HDA5 outputs. We're using the HDA5 Rust crate, which allows us to manipulate HDA5 files quite easily. So first, I need at creation time, so again, this is an encapsulated object. External users do not have access to the data members of this struct. They need to go through methods. For the constructor, I need to know where the file should be located, how large the simulation domain is. You will notice that this is the same configuration that I need when I create concentration grids. So we will need to sync that up somehow. And how many images I intend to eventually output. And given that, then I just call the HDA5 API to create a file of the proper name. specify that a data set inside of my SDA5 file that contains floating point data of the desired precision. I specify the chunk size to be 1 in the first dimension and rows and columns in the second dimension. So the idea is that the first dimension is our time dimension, and the other dimensions are our spatial dimension. And this means that later on, whenever I write an image, HDA5 will write immediately to the file, which will allow some, I don't know the English word for that, but in French, trafic en accordéon, where basically the HDA5 backend wrongly accumulates many images before deciding to write to the file, which will result in irregular I/O performance. And yes, I have tested that this chunk size is also optimal. And then I say how big my overall image will be. And then I just create it and name the dataset matrix. So notice this kind of API where I call methods of an object which return the object itself so that I can call more methods on it. It's called the builder pattern. It's very common in Rust. And if you've been careful in the previous sections, you may have noticed that iterator adapters are actually kind of an instance of this pattern as well. Finally, the last member of my data structure tracks how many images I have been writing so far and uses that when I write down some results to call the write slice method of the HDA5 dataset, passing the V concentration, which remember is the one we want to save, and indicating that we want to replace this particular slice of the data cube and we want to fully overwrite the spatial dimensions. And in the end, we can close the file. It's actually automatically handled inside of the destructor, but if you do it like that, then you get the same issue as with destructors in C++, where you cannot easily handle errors, which is why anytime you are thinking of having a destructor that could exhibit I/O error, I would strongly advise you to have this destructor as a last chance option, but also have an explicit method to close your file or whatever manually so that the caller can handle the I/O errors. And this is what the HDA5 library did, and I just exposed this choice on my side as well. So then, we can add that to our previous example. So first, I create my concentration buffer as before. Now I can create my HDA5 writer, passing it the shape of the concentration, the file name, which comes from some outside source, and the number of output steps. Then I run my simulation loop over some number of output steps. One decision of the reference C++ implementation that I have also kept in my Rust implementation is that we allow ourselves to run multiple compute steps for each output image that we store to the HDF5 file. This allows us to get a simulation that is compute bound and not IO bound. So for each output step, we run the desired number of simulation computational steps. Then we write a new layer to the file. And at the end, we close the file and handle the errors. I will not get into the details of error handling here, but we can discuss them more later if there's time. And finally, I provide, well, it's not finally, actually, I have a few more things to cover, but as you can see, nothing that I have written so far is specific to the actual implementation of our simulation kernel. So it would be desirable that we do not need to edit manually this code anytime we change the simulation kernel. We would like to extract the simulation kernel to a separate function. And we can do that actually by using the good old callback pattern, as you have seen earlier with the update method. So the idea here is that first I start centralizing all my simulation options into a data structure. Then I define a reusable run simulation function that takes these options as a parameter and also takes a user-specified callback that defines how the computation from the previous version to the concentration to the new version is done. Then I call back this inside of my compute loop. And finally, I get this reusable building block. And the user only needs to care about writing this callback, which specifies, how we go from the old concentration to the new concentration on each time step. Now, as I mentioned earlier, I would like all these parameters to be specified on the command line. And actually, that's surprisingly easy to do in Rust compared to what it's like in C++ or even other languages like Python, because we can use an excellent library from the Rust ecosystem called clap. And after adding it to our dependencies, which as usual is very easy, the way it works is we just import a clap trait called args for command line arguments. And then we can annotate our data structure declarations with some directives that tell clap what are the semantics of the command line option, like how do you specify it using a short option with a single dash or a long option with 2 leading dashes? What is the default value if the option is not specified? And we just say that, and there are also options for positional parameters and so on. We can opt, if we want, not to say it, and in that case, the names of the options are automatically derived from the name of the corresponding data structure members. And overall, so here I separate two kinds of options: the options that pertain to the simulation runner we've seen earlier, and the option that pertain to the actual computation of the gray Scott model. That's okay. We are allowed to define this as separate data structure because clap also has higher level constructs called the parser, in which we can flatten our command line arguments so that even though these two are separate data structures, to the outside world, it will act as one single set of command line arguments. And here again, I can specify some additional options for clap and what I would like my command line interface to be. And given this relatively small amount of annotation work, all I need to do in my program's main function is to just call the auto-generated parse method of this command line option struct. And that's it. I get automatically generated command line parser, which handles errors where you put a random string instead of a number in some numerical parameter, which automatically generates documentation when you type -- help when calling the program, generated from the doc comments of the data structures. It's super convenient. I wish we had that in other programming languages. The reference C++ code that this is derived from, again, had some hard-coded parameter. I kept them in as is in the Rust version for the reason of being competitive from a performance point of view, because anytime a parameter is hard-coded, the C++ compiler is allowed to leverage this to specialize the code for additional performance. And this is an occasion to show you some other Rust construct we've not seen yet called const, which allows you to define compilation constants. If you've ever used the thing called constexpr in C++, it's pretty much the same idea, but it also subsumes the functionality of constable in C++20. And we don't need const in it in Rust. Finally, I mentioned that I would like to have some progress reports, and this I can have using another nice library called indicative. It's really easy to use. After adding it as dependency, I can just import the progress bar type, create a variable of type progress bar specifying how many simulation steps I intend to have. And then I increment my progress bar on each computation step. And at the end of the simulation, I can declare to indicative that we are done. And that's it. So all of what you've just seen is already available in the exercises Rust project that you have downloaded at the beginning of this course. So I highly encourage you to go through the code, see if you can see how the various things I have shown in this chapter map into the source code that you have received. See maybe if there are some Rust constructs that you have questions about inside of this pre-made code. And then at the end, as an exercise to see if you have understood what's going on, I provide you with a naive implementation of the simulation update step, which I want you to use I want you to integrate inside of the simulation skeleton so that ultimately you can run the simulation with the following commands. I also, in addition to the main simulation binary, provide criterion macro benchmarks that you can use to measure the performance of the update loop alone without being polluted by, the I/O and other stuff that goes on in the full simulation. At this stage, it's expected that the simulation binary will take a few minutes to complete. Again, this code is really naive, and we will see in later chapters why it's naive and what we can do to improve its performance. I would finally advise you to use Git from this point of the course, because you will probably want later in the course to go back to previous versions of your work and compare performance, for example. And this will be a lot easier if you create one Git commit per course chapter. That's it from my side for this introduction. Now let's see what are your questions. So one question is self equivalent to this in C++? Not quite. We have, as I mentioned, two different versions of self, one which is lowercase and one which has a capital letter at the beginning. The capital version, unfortunately, does not exist in C++, and I wished it exists so many times. It allows you to refer to the enclosing type inside of the Rust equivalent of a class method. So for example, if you have a templated class, you can easily refer to this particular instance of the class with all the template parameters. And as someone else pointed out as a reply, the lowercase self is not quite equivalent to this in C++ either, because it does not have to be a pointer. It can be a reference, mutable reference, unique PTR. It can also be some more exotic Rust smart pointer types, even if I'm not sure if all of them are available on stable versions of the compiler right now. Overall, I would say the main difference with respect to this in C++ is that in C++ you have implicit usage of this, like you can refer to struct members and methods by just typing their name inside of a method, whereas Rust, like Python, chooses to be more explicit by having you type self.something every time, so that there is a clear distinction between what is a data member or member function and what is an external entity. Back to ownership in the UV shape, could you comment the let shape equals self.u.shape and why it's not illegal? It's not illegal because the shape method of ndArray returns an array of usize, and this array implements the copy traits. So then we can just take this shape and copy it as we want. Yeah, when it's returned out of the function, it's also copied out. I mean, basically self.u.shape returns the shape of the ND array by value. I'm not sure if that's clear.
Well, no, because it's not. So I didn't get it because yesterday you were saying that if I
no, sorry. Yes. Oh, so that's what you are missing. It returns a reference, actually. I missed that point. So the way I resolve this in my code, actually, because I must have faced this and found a way around it.
Sorry, could you please specify
And
which
so
line?
I can share the relevant code example. It will be clearer. So here we have this. So here we are taking the shape of self.u, which is an ND array. So we are actually, my mistake, borrowing the shape. So we would not be allowed so we could return a reference to this shape, but then whoever calls the shape method would end up borrowing self for as long as the underlying reference is being used. And I do not have the time to get into this, but it would be a bit limiting due to the way the ownership and borrowing Rust model works. So instead, what I do here is to take this slice of shape components and build an array out of it. And now, since I'm extracting usize out of the shape and building my own array out of it, there are no references anymore, so I don't run into any borrowing issues. Is that clearer?
Yes, it's clearer, thanks. But the thing that the shape 0 and shape 1 that you are creating inside this routine, as soon as you get out of the scope of the routine, they should be discarded. Or
they
am
are
I
not,
missing something?
because the indexing operator, when you call it like this without any reference qualifiers, it moves things out. And if the things are copied, it copies them out.
Okay, then you can return something like that.
If
And
I
then
want,
it will be owned by the guy that catch it.
exactly.
Okay.
If I wanted to return a reference instead, then before this shape 0, I would need to add an ampersand to say that I do not want to move out, copy out this value. I want to take a reference to it.
Okay, yeah, this is subtle and not trivial. Thanks.
Yeah, borrowing is a bit of a tricky concept. It takes a while to get used to. That's why I try to expose you as little to it as I can during this course so that you can get more time later on to get familiar with it yourself. As I mentioned earlier in this course, personally, I think it's one of those concepts in Rust that takes more than a year to fully grasp and master. Mosa points out that double buffering makes sense. She's seen, or he, I don't know actually. Anyway, that person has seen that people use different arrays as source or target depending on if the time index is even or odd, and yet that's an instance of the double buffering pattern. Again, you will also see it in computer graphics. I think that's where it comes from. You can, if you're that way inclined, you can think of it as a queue of length 2 where you override the old queue element. I mean, there are several ways to think about it, but in any case, yeah, it's a common pattern. It's a useful one to know. I understand there is no equivalent to the nice UV0, UV1 equal UV1, UV0 in Python to flip the references. You could do that with tuple patterns. I just didn't want to introduce these patterns, but that would look like this. The main difference here is that unlike Python, Rust wants you to explicitly manipulate tuples when you want to manipulate multiple variables at the same time. Eric mentions memswap. It does do something a little different. Memswap takes 2 mutable references as an input, and it allows you to swap the data that is pointed by those references, similar to std swap in C++. What is the concentration.shape type? It's an array of 2 U-size integers, as someone pointed out. ND array indexing versus HDF5 API. I guess time dimension is the most non-contiguous one. Indeed, I hope it is, because for compatibility reason, I had to copy the data layout of the C++ version, and I hope that my colleague who wrote the C++ version got this right. But generally, outside of Fortran and things that try to act like Fortran, most programming languages tend to use the last dimension as the most contiguous dimension in multidimensional arrays, and ND array follows this convention as well. I'm not sure if you have a way to put it into column manager mode. Maybe not. There is an equivalent argparse in Python for clear argument parsing. I've never seen one that worked based on the annotated struct declaration pattern. One nice bit about this one is, if I can show it again, is that you can specify the type of each thing, and then they will be automatically passed into the right type with proper validation of whether, the whatever weird string the user has typed in when calling your program actually is an integer of the right type, a floating point number, and so on. And it does all the things. So yeah, that's the nice part of it being based on data structures. It's that you can specify the type of each member's data structure using natural syntax for your static programming language. But maybe since last time I checked, Python got a library that worked that way.
Yeah, Adrien, maybe in the argparse Python package, you can define there's a type attribute to the command line argument parser. But you have to add it by argument for each argument. You need to define if it's a string, an integer, or float value, Boolean value, and so on.
And the nice part here is that you can just start by declaring a struct using natural syntax, and then later turn it to an argument parser without adding type metadata. I don't know if that is clear.
That's the advantage.
Someone posted a link to something, but given that my internet connection is behaving very weirdly this week for some reason I don't understand, it will be a while before I get the chance to open this link actually. Meanwhile, we look at other questions. Is there a crate with a full Rust HDF5 implementation? I don't know how feature complete the HDF5 crate is. It's been complete enough for my needs so far, but I've not pushed it as far as some advanced HDF5 users would. In any case, this binding to the HDF5 library uses a pattern that's quite common in Rust bindings to C or programs, which is that you have one low-level binding that simply replicates the underlying C library. So to use it, you need lots of unsafe code with row pointers and that stuff. And then on top of that, there's a higher level binding. And normally in this sort of two-layer projects, the low-level binding is typically automatically generated, so it's perfectly feature complete. And the high-level binding is written by hand to match idiomatic Rust patterns and make it possible to use the C library with only safe Rust patterns. And that takes time and human effort, so that might not be as in sync. But I don't know how in sync it is. I have never found a place where it was not feature complete enough for me. So meanwhile, the thing has loaded. So I see that click in Python works by annotating functions with command line parameter metadata. So I guess that's, yeah, it's already nicer than other Python argument parsers I've seen, but still you would need to probably to annotate your type manually. I don't know if it can handle Python 3 typing annotations. Yeah, I don't know it well enough to compare this one. So is const a compile time or runtime construct? It's slightly unclear to me. So the thing is, one of the most misunderstood aspects of constexpr as it was initially released in C++11 is whether it occurs at compile time or runtime. So you're not alone in being confused by this. Const in Rust, for the most part, copies the semantics of constexpr in C++, which means that, for example, if you have a constexpr const function in Rust, you can call it either at compile time or at runtime. The difference is that you can use it to compute quantities which need to be known at compile time, like the size of arrays, and you cannot use regular functions for that. However, where people tend to get things wrong is assuming the compiler actually has the option to call const code in Rust, constexpr code in C++ at runtime. Will it do so or not? And actually, in the original constexpr concept, that's left up to the implementation, and Rust copied that. What Rust did, and I actually think that some variant of it could exist in C++, but I've never seen people use it, is that you can do this. For example, egal, and if you declare a constant like this, you have a guarantee that the value of x will be computed at compile time. And because people felt this was a bit too verbose, later on it was shortened into this in recent versions of the Rust compiler. So now you can just have a const block in which you can call constfn, and you have the guarantee that the value of the expression of this const block will be computed at compile time. So this effectively implements the equivalent of consteval in C++, where you want to guarantee that the value will be computed at compile time or the compilation will fail. Hope that makes sense. Could you explain in this command cargo run -- release that has been simulate -n5e2 how does cargo find the simulate executable and what is the double dash? So cargo works a bit like Git, if you've ever used that. The way Git works is Git has internally to each repository some .git hidden directory that contains all of its metadata used to store multiple versions of the code and so on. Cargo works similarly, but instead of looking for a .git folder, it looks for its configuration cargo.toml. So cargo will recursively go up parent directory by parent directory, looking for a cargo.toml to find its configuration. Once it's found it, then it knows what is the root of the crate, let's say library or program project. And from this route, then it will find the source code for the simulate binary, because Cargo uses some standard directory structure by default. So you have something called the Cargo book that you can find over this URL, which explains this sort of stuff. But essentially, by default, Rust encourages you to sort your source files in a specific way. If you don't want to sort them in that way, then you will need to have more involved configuration entry where you say, oh, I define a new executable, the source file for it is in that place, and so on. What is the double dash? So the double dash is a common Unix convention for tools, command line utilities that are meant to wrap other commands. Here, I'm running Cargo with some arguments that are options to Cargo itself. And then at the end, I'm passing options to my simulation, like how many images I want to generate, how many compute steps I want to run per image, and so on. And the problem is I need to tell Cargo, okay, some arguments are for you, some arguments are for the program that you will be running after compilation. And the double dash is kind of a standardized separator in the Unix command line community to express this. Hope that's clear.
Yes, thank you.
After the course has finished, will the code run by us still be accessible and running in our containers? I heard something about Devana. So probably you will not keep your Devana users account forever. I don't know what's the local policy here. I think Joseph or Michal would be the one to know of the current audience. But the container is something that you download in on your computer and you can keep using it forever. It's kind of like a virtual machine image. It's not running in some server in the cloud.
Yeah, thank you. And is it possible then to like easily make this code run on our CPUs?
Indeed, it is. If you remember the environment setup section of the practical work, it had 3 variants. I will share this to show it. Screen sharing. Sometimes I wish I had 2 computer screens. So when you go to the environment setup section here in the menu on the right-hand side, you get multiple options. One is to use a Devana cluster if you've been granted access to it. One is to use Linux containers for a pre-built environment. And one is to just manually install the required packages on your computer. If you click there, you get a list of everything that's used by the practical work, as well as some other thing that we don't strictly need, but I would strongly advise you to have. And then you get operating system specific steps. So for Linux, you get one package manager instruction per family of Linux distribution, because Linux distributions are a mess. And after you've installed all the native C and C++ packages in that way, then you get the Rust installation, which is the same for every Linux distribution. Actually, it also works on macOS. And how to install the data2pix utility to render images. And some quick tests to check that your environment is working.
Thank you very much. And to just clarify and recall, all this course is accessible later also. Yeah,
Indeed.
So we can get back to these instructions and just you don't have to save it in any way. Okay,
the intent is to keep them available forever. They may be updated at some point, when I prepare the next edition of the course, but
thanks.
They will remain available. What is your, sorry, I did a Zoom mistake. what is your favorite profiler to use and potentially your workflow for profiling Rust code produced specifically for running on a cluster? Personally, I actually am more specialized in the optimization of code that runs on a single compute node than in distributed computing, which means that I have more expertise in the profiling of this kind of code. And for this kind of mono machine execution, my favorite profiler on Linux is Perf, because it works on every CPU that I have tried it on. It's extremely powerful. You can make it measure so many different things. Its main issues, in my opinion, is that the documentation is pretty poor. And I actually fixed that issue for my French colleagues and myself by writing a very in-depth tutorial to it in French that I intend to translate to English later when I get time, hopefully next year. For cluster profiling, I would advise studying the kind of tools that people use in the C, C++, Fortran community, because these tools operate using debug information, typically dwarf inside of ELF binaries. And this is actually common between Rust and the other languages that are compiled in an ahead of time fashion. So I expect that probably any tool that's able to do distributed profiling for C, C++, Fortran should probably work for Rust, even if suboptimally. I will just, by the way, in case we have some French people around, also put the link to my current Perf practical. This one is meant to run on a machine that I self-host, so you will need to adapt the instruction to run it on your local computer, but I mean, it's better than nothing, which is what you get when you try to look for the documentation of Perf. The problem with const expr in C++ is that it can only handle transient allocations only in scope blocks, so that the destructor will be called. Yeah, actually in Rust, that's worse. I think we don't yet have dynamic memory allocation in const yet on stable versions of the compiler, but there is effort underway to fix that. I would argue, however, that sometimes people tend to overuse a little the const expr functionality in C++ and the const functionality in Rust today. And it's important to always keep in mind that not every computation needs to be done at compile time, and that the more work you shift to compile time, the more you risk running into a situation where your compilation takes a long time to run, consumes a lot of memory, and working on your program becomes a bit of a pain. Hope that kind of addresses your comments. So it looks like the questions have quieted down. I mean, calmed down. So maybe I will leave you work a bit, and then I can move on to do some kind of corrections of the first parts of the Gray Scott exercises. Yes, something else that I got by email. So yesterday, you may remember that Matthew mentioned he was puzzled by the exercise of the ownership chapter because he did not get a significant speed up out of it. And that was a bit of my mistake, actually. The problem is I initially wrote this exercise in a certain way. Then as I wrote later part of the courses, I realized that I needed to write the exercise in a different way to be able to get the effects that I wanted you to study. And so I changed the exercises in some places in the material, but not everyone. So the result was material that was a bit confusingly worded, a bit hard to read, and I apologize for that. I think I have fixed all occurrences of this, and in addition, I have improved the wording of the question of the exercise. And by following the new wording, Matthew did observe the expected nice speed up from the optimization introduced in this chapter, 5 times, 10 times speed up. I'm sorry, actually, did I open my mic when I said this?
Yes, yes.
Okay, cool. So I see that we have a, I'm not sure if it's a question or a comment, that there are some compiler errors due to use. Were there in the initial code or after you started modifying it, maybe?
Well, when I cut and paste your program from
Oh,
the,
yes. So
and
probably
then
I missed some use statements in my snippet. This sometimes happens because these ones I cannot automatically test in my CI, unfortunately.
yes, I guess.
I will check out, but anyway, the compiler should probably have suggested the right use statement to you, which is some really nice thing.
Exactly, yes. It saved my day.
That's one
But
nice
then
thing about
the thing
Rust,
that
is the
we have
compiler
to
is
do it,
helpful.
yeah, but we have to do it twice, so that I was surprised. So is it normal that we have to do it twice?
So you mean twice, once in source bin simulate and once in benches? Well, yes, because use only affects the current code module.
Yes.
And these two files are different code modules. In fact, they are even different binaries. However, I think that's not your question. When you said we have to do the work twice, what I would advise is for you to put the compute backend inside of the library in SRC, in the SRC directory of the examples source code, so that you can then use it from both the benchmark and the main simulation binary, if that makes sense. If not, I can just show you how that's done.
Yeah, I think I got it. Okay, thanks. But then maybe that's why I'm getting this
It
compile
might
error.
be. Maybe my code is correct only if you are in the context of the use statements of the surrounding program.
Okay, good. Thanks a lot.
So I would propose that for once we actually take our middle of session break at the scheduled time. So what I propose is I will be away from like 20 minutes getting my favorite hot beverage. I advise you to do the same, clear up your mind, but if you want to continue working on the exercises, that's fine as well. And when we start again at 2:50, then I will get into some corrections of the first parts of the discourse so that we can move on to the next steps.